Hello everyone and welcome back. In the previous session, we have learnt about the instructions which deal with the OR logic. In this session, we are going to learn about the instruction types XRAR and XRID8. These two instruction types deal in exclusive OR logic. So without any further ado, let's get to learning. Coming to the topics that we are going to cover in this session. At first, we will learn about the basics of exclusive OR or XOR operation. Thereafter, we will learn about the first instruction type of the day, that is XRAR. Finally, we will conclude our session by learning about the instruction type XRID8. So let's begin with the first topic, the basics of exclusive OR operation. Now, before we learn about the basics of exclusive OR operation, let me remind you the 8085 microprocessor provides the instructions which support the logical operations like AND, OR, exclusive OR, and NOT. From all these four, we have already learnt about AND and OR. I hope you remember the instructions ANAR and ANID8 deal with the AND logic, whereas coming to OR, the instructions ORAR and ORID8, these two deal in OR logic. Today we are going to learn about the exclusive OR, and just like AND and OR, exclusive OR is also a binary operation. That means it includes two different operands. Now just like AND and OR, in case of exclusive OR, the first operand is bound to be inside the accumulator. Coming to the second operand, in this case as well, just like the previous two, we have got three different ways to provide the second operand to the 8085 microprocessor. The first way is we can store it as the contents of the GPRs. That means any of the general purpose registers. Coming to the second way, it can become the contents of the memory location which will be pointed by the HL register pair. In general, we are talking about the memory element which is represented using the M alphabet. And the third way is we can send the second operand as an 8-bit immediate data via the instruction itself. Now let's get into the basics of XOR operation. As I told you earlier, exclusive OR or XOR is also a binary operation, so it includes two different operands. Let's assume we have got two operands X and Y. Now with two operands, you already know we can have four different combinations as inputs: 0, 0, 0, 1, 1, 0, and 1, 1. Now if we talk about the XOR logic, it means exclusive OR. If you remember in the previous session when we were learning about the basics of OR operation, I told you OR is also called inclusive OR. And the reason behind that is it includes the AND logic as well. That is, when both the inputs are high, in case of OR, the output is also high. And that's the logic of AND. Now coming to exclusive OR, it actually excludes that AND logic. So in case of exclusive OR, if and only if the inputs are alternating bits, that is, either X is 0 or Y is 1, or X is 1 and Y is 0, in these cases, the outputs are going to be 1s. On the other hand, if the inputs are same, in that case, the outputs will be 0s. Notice, in case of XOR, we excluded the AND logic. Previously for OR, for the inputs being high, I'm talking about both the inputs, the output was also high. But that's not the case for exclusive OR. Due to the reason that this function excludes the AND logic, it is known as exclusive OR. Now this is the truth table of exclusive OR, and I believe you have seen it multiple times when you have studied about the digital electronics. However, today we are going to look at it from a different perspective. At first, consider these two rows. Notice, as we have reset the input of Y to 0, whatever value we are sending via X, in the output we are getting the same value. So from this we can state X exclusive OR 0, that is Y is being reset to 0, it will always generate X. So clearly, no matter what we send via X, the same input will be propagated to the output if and only if the second operand is reset to 0. Now notice, if we consider these two rows, observe, when Y is set to 1, the input X, which is 0, is being inverted as the output. Notice it is 1. Similarly, if via X we are sending 1, the output is now 0. So basically, we can state from this, X XOR or exclusive OR 1 will generate the complement of X. So clearly, no matter what we send via X, if the second operand is set to 1, as the output, we will get the complement of the input. Now let me tell you another thing. Due to these two logics, exclusive OR is also known as controlled inverter. Notice, if we reset the second operand to 0, the output is same as the input. On the other hand, if we set the second operand to 1, the output is the complement of the input. So we can control the inversion by setting the second operand. Anyway, using this particular logic, we can selectively complement the bits of accumulator. I hope you remember, in case of AND, we could selectively reset the bits within the accumulator, whereas in case of OR, we could selectively set the bits in the accumulator. Now coming to exclusive OR, using these two logics, specifically the second logic, we can selectively complement the bits of the accumulator. Now how we are going to do that? Let me give you one example. Say we would like to complement the least significant bit of the first operand, which will be already there inside the accumulator. And in order to do so, we have to choose the second operand a bit carefully. Can you guess what will be the second operand? Well, the second operand will be all zeros followed by the least significant one. Because we only want to complement the least significant bit of the first operand, so for that bit, we are having 1 as the least significant bit of the operand 2. Now coming to the rest of the bits, we don't want to alter them, so for those, we will have zeros. So clearly, the operand 2 for this purpose is going to be 7 zeros followed by 1. And this is how we can selectively complement the bits, because after the operation has been performed, the result will also be loaded inside the accumulator. Now just like AND and OR, exclusive OR operation is also going to affect the flags register. Now think about it. Exclusive OR is just a variation of OR. So similar to OR, here also the carry and the auxiliary carry flags are to be reset always. Now coming to the rest of the flags, parity, 0 and sign, these will be affected by the contents of the accumulator. I hope you remember, parity is to be set if within the accumulator we have even number of ones. Coming to Z flag, it is going to be set if within the accumulator we have got all zeros. And sign flag will be set if in the accumulator the most significant bit is 1. So do remember, using the exclusive OR operation, we can selectively complement bits of the accumulator. So that was all about the basics of exclusive OR operation. Let's now learn about the first instruction type of the day, XRAR. Now coming to the instruction type XRAR, it stands for exclusive OR accumulator with R. Notice, in the mnemonic XRA, the X is coming from the X of exclusive, R is coming from the R of OR, and A stands for the A of accumulator. So as mentioned in here, the first operand will reside inside the accumulator, and we are going to perform exclusive OR between the accumulator's content and R. Now what is capital R? I believe so far you already know this. It will include the accumulator register, all the general purpose registers, and along with them, the memory element which will be pointed by the HL register pair. Now since exclusive OR is just a variation of OR, So here also, both the carry and the auxiliary carry flags are to be reset. Coming to the remaining flags, these will be affected based on the accumulator's content. Now, if we talk about the XRAR instruction size-wise, this will fall under the 1 byte long instructions category. Now remember, XRAR is the instruction type. We will have different instructions of this particular type, and these instructions are going to be XRA-A, XRA-B, C, D, E, H, and L, that is all the general purpose registers. Along with that, the XRA-M, that is the memory element which will be pointed by the HL register pair. Now let me tell you about something really interesting. We already know if both the input bits are same, in that case, exclusive OR will output 0. So what do you think will happen if this instruction, that is XRA-A, is executed? Say within the accumulator we have some content, and with that content, if we XOR that content itself, what will be the outcome? Well, you guessed it right. XRA-A can also be used to reset the contents of the accumulator, or in other words, the execution of the instruction XRA-A will convert all the bits within the accumulator to zeros. And the reason for that is we are performing exclusive OR of the same bits. Let me now show you an example of how this instruction is going to work. Say within the accumulator register, we have got the value 1, 2. And within the E register, that is the general purpose register E, we have got the value AB. Now if the instruction XRA-E is executed by the microprocessor, the XOR operation between 1, 2 and AB will be performed. Now the binary equivalent of 1, 2 is 0, 0, 0, 1, that is the 4-bit equivalent of 1, which will be followed by 0, 0, 1, 0, that is the 4-bit equivalent of 2. Coming to AB, the 4-bit equivalent of A is 1010, which will be followed by 1011, that is the 4-bit equivalent of B. Let's now perform the exclusive OR operation. Remember, the outcome will only be 1 if we have alternating inputs. That is, either of the bits should be 1. In case both the bits are same, the output is going to be 0. Let's now consider the least significant nibbles at first. So we have got 0, 1 in here. So the output is going to be 1. And the reason is the bits were alternating bits. Now notice here we have 1 in both the cases. Also in the next place we have got zeros. So for these two, the outputs are going to be zeros. Remember, for same inputs, in case of exclusive OR, the output is always zeros. Finally, here we also have alternating bits, just like the least significant bits. So what will be the output? 1, right? So this is going to be the outcome if the exclusive OR is performed between these two nibbles. Let's now focus on the most significant nibbles. I hope you remember how the logic is going to work. For alternating bits, the output will be 1. And for the same bits, the output is going to be 0. Notice, here we have got alternating bits. And in the next place also, we have got alternating bits. So for both of them, the outputs are going to be 1s. Coming to the next place, we have got zeros. So the input bits are same. So we will have 0 as the output. Now if we talk about the most significant bits, these are alternating bits. One of them is 0 and the other is 1. So the output is going to be 1. So after the execution of XRA-E, remember, before the execution of this, within A register, we had the value 1, 2 or 000 followed by 1 followed by 0010. And within the E register, we had AB 1010, 1011. These 8 bits. Thereafter, when we executed this instruction, the output is going to be this. Now in hexadecimal, can you figure out what it will be? 1011 is 11 of decimal. So in hexadecimal, it is B. Coming to 1001, it is 9 in case of both decimal and in hexadecimal. So after the operation has been performed, within the accumulator, the value B9 will be updated. And do remember this fact, we are using this hexadecimal notation for our readability. Within the accumulator, in reality, this value will be stored. That is, the 8 bits. Let's now talk about the situation of the flags register. Now, as I told you earlier, exclusive OR is also a variation of OR. Therefore, both the carry and the auxiliary carry flags are to be reset. Now, what will be the situation of the parity flag? For this to be set, we already know within the accumulator, we should have even number of ones. Now, do we have that? Let's count 1, 2, 3, 4, 5. 5 ones. Now, 5 is an odd number. So clearly, the parity flag will be reset. What about the Z flag? The accumulator's content is not all zeros, so the Z flag will also be reset. Coming to the sign flag, the most significant bit within the accumulator is 1, so the sign flag is going to be set. So this is going to be the status of the flags register after this operation has been performed using the instruction XRA E. Now why exactly we chose E? Because the second operand was residing inside the general purpose register E. So this is all about the instruction type XRAR. Do remember, this instruction falls under the 1 byte long instructions category, and due to the presence of R within the instruction type, it is evident that there are 8 different instructions of this type, to be precise, 8 opcodes. So that was all about the instruction type XRAR. Let's now focus on the instruction type XRID8. Now coming to the instruction type XRID8, it stands for exclusive or immediate with accumulator. So clearly, first operand will be inside the accumulator, and the second operand we are sending via the instruction itself. Now if we talk about the mnemonic XRI, observe, the X of XRI is coming from exclusives X, R is coming from the R of OR, and I is coming from immediates I. Now here also, we are trying to implement the XOR logic. So clearly, both the carry flag and the auxiliary carry flags are to be reset. Coming to the remaining flags, these are to be affected based on the accumulator's content. Let's now talk about the instruction type XRID8 size-wise. What do you think? In which category will it fall under? Well, D8 specifies data of 8-bit. Now XRI is going to need 8 bits, and we are also sending 8 bits of data through the instruction. So in total 16 bits, and 16 bits is 2 bytes. Therefore, this instruction will fall under the 2 byte long instructions category. Now do remember, in this instruction type, we are sending the data in immediate addressing mode. We are not keeping it in any of the registers, that is the general purpose registers as well as the accumulator. Neither we are keeping the second operand inside the memory. Therefore, for this particular instruction, there will be a single opcode. Now let me show you an illustration for better understanding. Just like we mentioned earlier, here also the first operand will be residing inside the accumulator. So let's say within the accumulator register, we have got the value 45. Now coming to the second operand, via this instruction type, we are going to send the second operand to the microprocessor through the instruction itself. So let's try to execute the instruction XRIF3. Notice, this is the second operand. So execution of this instruction will perform the XOR operation between 45 and F3. Now coming to 45, the binary equivalent of this is 0100, that is the 4-bit binary of 4, followed by 0101, which happens to be the 4-bit binary of 5. Let's now convert F3 to its equivalent binary. F is 4 ones, which will be followed by the 4-bit binary equivalent of 3, which happens to be 0011. Let's now perform the exclusive OR operation. Remember, when the bits are same, the output is 0. Only in case of alternating bits in the inputs, the output is going to be 1. Now notice, in the least significant bits, we have got the same bits in both the cases, that is 1s. Therefore, the output is going to be 0. Now notice the next two consecutive bits. In both of them, we have got alternating bits. So the output is going to be 1, 1. Finally, these two bits are same. So the output is going to be 0. So this is going to be the outcome if we perform the XOR between these two nibbles. Let's now focus on the most significant nibbles. Notice we have got alternating bits in here. Therefore, the output will be 1. Here also we have got alternating bits. It is 0 and this is 1. So we will have 1 once again. Now these two bits are same. Both of them are 1s. So the output is going to be 0. And finally, if we talk about the most significant bits, these are 0 and 1. So alternating bits, therefore the output is 1. So after the execution of the instruction XRI F3, and do remember beforehand we will have within the A register the value 4, 5. This will be the outcome. Now can you figure out what it will be in hexadecimal? Well, 1011 is B and 0110 is 6. Therefore, within the accumulator after the operation, the value B6 will be loaded. Let's now talk about the flags register. You already know since XRI is a variation of exclusive OR, therefore the carry and the auxiliary carry flags will be reset. Coming to the parity flag, this will be set if we have even number of 1s, but let's see whether we have it or not. 1, 2, 3, 4, 5. Now 5 is not an even number, it's an odd number, so the parity flag will be reset. What about the Z flag? Evidently, since we don't have all zeros within the accumulator's content, this will too be reset. What about the sign flag? Notice, the most significant bit decides the sign flag, and since it is 1, therefore the sign flag will be set. So this is going to be the status of the flags register. So that was all about the instruction type XRI D8. Do remember, this falls under the category of 2-byte long instructions. Additionally, since we are sending the second operand via the instruction itself, therefore, there will be only a single opcode for this instruction type. So in this session, we covered the topics. At first, we learned about the basics of exclusive OR operation. I hope you will remember that the exclusive OR or XOR logic is also known as controlled inverter. If we set one of the operands as 1, the outcome is going to be the complement of the neutral operand. That is, the operand which we haven't set to 1. Then we learnt about the instruction type XRAR. This instruction type falls under the 1-byte long category, and there are 8 different opcodes or instructions for this type. Finally, we learnt about the instruction type XRI D8. This instruction helps in sending the data using immediate addressing mode. So for this instruction, only the accumulator is to be loaded by the first operand. The second operand will be sent via the instruction. Additionally, this instruction falls under the 2-byte long instructions category, and there will be a single opcode for this type. Alright people, that will be all for this session. In the next session, we are going to learn about the instructions which involves the NOT logic. So I hope to see you in the next one. Thank you all for watching.